899983937. Voice call.
Sir, recording has been started, sir.
Okay, yes, very good. So now I can let me just close this off. Yeah. Okay. Okay, good afternoon, everybody. Let's start where we left off the previous lecture. So that this theorem we stated day before yesterday, extra is compact, Hausdorff locally compact, and this is an open embedding. So proof of the above theorem, I don't seem to have written anything here. We proved compactness. So let me recall how compactness was proved. So okay, I'll show it with a picture, and your job is to convert it into writing. Let me use some different color. So here is how X looks, and it has an extra point added to it. Okay. And that is the point star, also called infinity. Infinity is a nice name, as you have seen from our previous example of Rn. Okay. Now I want to show it is compact. So X, okay, this is too faint. X compactification equals X union this point at infinity. I want to show it's compact. So suppose there is an open cover. UI is an open cover. Then the point at infinity, the point star, this is equal to star. I'll use either name interchangeably. This belongs to one of them. So let's rename that particular as U0. Okay. Now, what does it mean that U0 is an open set containing star? That means U0 is equal to X minus some compact set with the point star added to it, because that was the definition of open neighborhoods of infinity. Open neighborhoods of infinity were complements of compact sets. Here is a compact set, C, and its complement is the open neighborhood at infinity. So X belongs to this U0. But now C is contained in X star, of course, and which is the union of all these UIs. And this is compact. So this shows that C is contained in, after reindexing, C is containing some U1 union to N. And that means X star is therefore U0 union U1 union UN, because U0 was X minus C union star. So whatever is not in C is already in U0, and C is in this stuff, so together they cover everything. That's why it's compact. Next point is, if it is compact, then this is proper, and that we did by this graph factorization. This was the graph map. And this graph map is a closed embedding because Y is Hausdorff. Okay. All our spaces are Hausdorff. So this is a closed embedding because Y is Hausdorff. Okay, because what is the graph? Well, the graph is the inverse image of the diagonal of Y. This is X cross Y, this is Y cross Y, there is this map. If that map was called F, then this is F cross identity. And here is diagonal of Y. And its inverse image is this graph of F. This is closed, so its inverse image is closed here. So this closed embedding, therefore proper. This is proper because X is compact. Composite of proper is proper. So this is proper. So we said closed embeddings are proper. Again, no proof is written here. Why are closed embeddings proper? Because if X, Y is a closed embedding, suppose this closed embedding F is a closed embedding, then X cross Z is also closed embedding in X cross Y. This is also closed embedding. Or in more plain terms, if X is a closed subset of Y, then X cross Z is a closed subset of X cross Y. So this base is after taking product, it has remained closed, so it is proper. Then here was a statement, if X to Y is proper and Y is compact, then X is compact. Because Y is compact, the map to a point is proper, and X to Y is given to be proper, so the composite map to a point is proper, and a map to a point is proper if only the space is compact. If X to Y is proper, then the inverse image of any compact set is compact. Why? Because if X to Y is proper, you take any subset here and take its inverse image, that map is again proper. Now C was compact and here to here is proper and C to a point is proper. So the composite is proper and therefore inverse C is compact. You see, again and again we are using just factorization properties, graph, diagonal, such things. This said, if X and Y are locally compact under F to Y, the inverse image of any compact subset is compact, then F becomes a unique map sending star to star. So define the map sending star to star. All that you have to check is that it is continuous. It was continuous anyway from X to Y. So now you want to check continuity at infinity. So if I take a neighborhood of infinity in Y, which looks like this, its inverse image under this prolonged map is this neighborhood of infinity here. So inverse image of those open neighborhoods of infinity or open neighborhoods of infinity in X, and therefore it is also continuous at infinity. So it's a continuous map. At this point, one of you, not at this point, later one of you, I think Arnab, asked a question that what is it therefore functorially? And I told you that. And so I'll say something just now which I am not explaining. This you may understand later. 1 point compactification is a functor from locally compact Hausdorff spaces to, this is a category of locally compact Hausdorff spaces and proper maps. This is one category. Okay, because anytime I have two locally compact spaces and a proper map like this, inverse image of compact is compact amounts to proper, as you will see from the next theorem. Then there on the other side is the category of pointed topological spaces. This is what it means. Okay. So that's because I said proper here instead of saying inverse image of compact is compact, because these two are equivalent for locally compact spaces. And that is proved here. It has a very simple proof. Again, a very diagrammatic proof, because okay, so that proof is just by base change. This is proper because this is compact and this is compact, and any map from compact to this is proper, one of the earlier statements. So its restriction to Y is proper, okay, and which is what you have been asked to prove. And if it is proper, then you can see that it extends from X star to Y star, etc. Okay. Then we asked when is a map from Rm to Rn proper, and there are three equivalent conditions. Its being proper is the same as inverse image of each bounded subset is bounded, and same as limit as mod x tends to infinity is infinity. I orally explained the proof, and it was your job to write down the proof, which perhaps some of you have done. And if I have a non-constant polynomial, then the resulting map from complex numbers to complex numbers is proper, because limit as z tends to infinity of fz is infinity. So one of the equivalent conditions of properness from Rm to Rn is R2 to R2, the map from C to C. Then I asked you for a linear map, when a linear map is proper, and when is it open, when is it closed, etc. So it's open if and only if it is surjective. Closed, well, if it's an injection, then it is closed, and there's one extra special case. Any vector space mapping to the zero vector space, one point vector space, is a closed map. Otherwise, injections are the other closed ones. When is F proper? Closed injections, closed embeddings are proper. We already seen that. And this is not proper if M is greater than or equal to 1. Then we talked of the inverse function theorem, openness criterion, that if I have a differentiable map whose derivatives are also continuous, all partial derivatives, F is continuous, all its partial derivatives are continuous, it's defined on an open subset of Rn, it's a map to Rn. When is it open at a point? So this was the case of a globally constant, meaning linear map. Linear map is just that same matrix everywhere. While here the derivative keeps changing, and that's given by this Jacobian matrix. And this map is open at a point P, which means it takes a small open neighborhood of P to an open set in Rn. If the following sufficient condition is satisfied, this condition is not necessary, but sufficient. So if the rank of A is M, then this map is open. After that, I gave you Narasimhan's proof. So Narasimhan was my thesis advisor. Okay. I learned this proof from him many years after I finished my PhD with him. And he said that it's very simple by properness. He just said one or two sentences. So I'm telling you the details. So if I have a non-constant polynomial, then the resulting map is surjective is the statement of the fundamental theorem of calculus. If I write this function as real part plus imaginary part, then the Jacobian matrix looks like this. And by Cauchy-Riemann equations, this determinant, this term is this term and this term is this term. So together, this determinant becomes this square plus this square. And both are real, they can't cancel each other. So this determinant is 0 if and only if f prime z is 0. And this is f prime z because I can differentiate with respect to the real change in z. I can move z by adding a real h to it. And then this resulting derivative is just the partial derivative, which you would have called df by dx. Okay? Add z. And which is this? F prime is this, and this is this. Okay. So that shows that when the derivative is non-zero, f is open at P. Now, derivative is also polynomial. It's of degree 1 less. And I'm taking it to be a non-constant polynomial, because if derivative is constant, what is f? Yeah. Fz equal to az. This definitely has a 0. Z equal to 0 is a root. So you can have prime non-constant. I need not insist that is non-constant. Nowhere do we use it. But okay, so if f had really degree 1, I am through. Or a z plus b. If it was of this time, then of this type, that's also degree 1. Then the root, and I have taken a monic polynomial probably. Doesn't matter. So then you know that this has a solution, namely z equal to minus b upon a. So assume non-constant. Assume this is greater than or equal to 1. for this reason. Okay, so how many roots can it have? It can have n-1 roots at the most. Okay. And then I take the set of all roots of f prime, I take its image, it has at most n-1 point, and I take its pre-image. How many points can map to those n-1 point? To any point there map at most n points. And so this is again a finite set. After I remove this finite set from here, the image goes in C minus this set. And this is a restriction of the original map to this open set and its inverse image. And this map we said is proper, therefore this map is proper, therefore it is surjective. Sorry, how do I know it is surjective? This is proper, so it's closed. Also it's open because at all these points the derivative is non-zero. So it's open and closed. This is non-empty because it's only a finite set removed from C. And this is connected. So if I have some open and closed and non-empty subset, namely the image of this in this, that image has to be everything. Why is this connected? C minus any finite set of points is connected. R2 minus any finite set of points is connected because you can go from anywhere to anywhere avoiding those finitely many points. So this is surjective. And this is dense here. So the image of C is dense here, and this is closed map. So image is everything. So F is surjective. So that's the proof. And so the only thing I didn't do in my previous lecture was tell you why it is locally compact at infinity. I started writing the proof. I made a mess of it. Then I gave it another shot, but then I said I'll do it next time. So let's do it. And so after the lecture, I thought about it and realized that it's very easy if I do it in 2 steps. So here's the first step. If X is Hausdorff and K contained in X is a compact subset and P belongs to K, then there exists an open subsets U and V in X. So that K is inside U, P belongs to V, and U intersection V is empty. How do you prove it? So here's my compact set K. Here's the point P. And now for every point here, because it is Hausdorff, for every point here, there is an open neighborhood here, and there is an open neighborhood here, which are disjoint. But finitely many of these open neighborhoods cover K. And I take the intersection of the corresponding finitely many neighborhoods. Intersection here. Of VIs, let's call them VIs. And these are the UIs equal to V. And union of the UIs equal to U. And these are finitely many.
Sir,
Yeah.
hello?
Yeah.
So P belongs to K.
P doesn't belong to K. What should I said it the other way around. Sorry. P does not belong to K. I do the picture correctly. I think in pictures rather than prose. So trust my pictures more than my writing. Okay. So property of all geometers. All right. So yeah, now is it clear? Was that Arnav? Who
Yes,
pointed
sir.
out the misprint? Thank you, Arnav. Thank you for pointing out the misprint. Okay. So this proof actually, I asked you once, meaning all you students, and Ishan gave this proof in class. Anyway, so this is clear to you. Now we can apply the above to show that if X is a one-point projection of a locally compact Hausdorff X star. If X star Hausdorff space X, then every open neighborhood of star contains a compact set C and an open set V with star belonging to V contained in C contained in what? What was the other one called? U. In every open neighborhood U. So I need to make some space here. every open neighborhood U of star contains blah blah blah. Yeah, this is the meaning of. So again, a picture will make it clear. So here is X, and here is this star, and I have been given an open neighborhood here. Let's call it. Okay, I have been given an open neighborhood of this. Let's call it U. So I have to paint my U in some color. I'll paint it. This is U. Okay, this is the color of U. This is U. U. And star belongs to U. Okay. But what is an open neighborhood of infinity? That means its complement, which I'll paint in some other color. This is compact. This is K. So K is compact. Because open neighborhoods of infinity are complements of compact sets in X together with that extra point, star. So K is compact. Okay. Now, because K is compact and star is not in K, because star was inside U and K is the complement of U. So we are in this situation that I have K now instead of X applied to X star, which we have shown is compact. And so I have point not there, and so there is a neighborhood and a neighborhood of P which are disjoint. So, so this neighborhood, what is the neighborhood of K? So here is the neighborhood of K which is disjoint from a smaller neighborhood of X. I have already chosen some name for the neighborhood of X. Okay. So, that name was unfortunate. So there is some neighborhood of K, and this is an open set. Open. This is an open. And inside that, there's a neighborhood of star. This is a neighborhood of star. Okay. So what does neighborhood of K mean? An open set containing K. So the complement of that is a compact set because X star is compact. So if I take this open neighborhood W, this is the open neighborhood of K, then X star minus W is closed in X star. So X star minus W is compact. And this neighborhood is disjoint from this tiny neighborhood here, which I'll call as W prime. And so I have achieved my desired thing, that this star belongs to W prime is contained in X star minus W is contained in X star minus K. Okay. So this was the given open neighborhood you started with. This is a compact set we created, and inside that there's a neighborhood, and inside that there's a point. So we have shown that it's locally compact at infinity. This was the proof that I just studied nest, and so I have given it to you. Okay. Now let's define this important concept, action of a topological group on a topological space. This definition, very, very important in mathematics, is this. You know what's a group action in sets. In sets, in every category, okay, not every category, in all kinds of categories in which there are binary products, terminal object, initial object, etc., etc. In all such categories, you can have a definition of group appropriate to that category, and they are respectively known as abstract groups if it is sets, topological groups if it is topology, Lie groups if the category is that of differential manifold, analytic groups if it's holomorphic manifolds, algebraic groups if those are varieties, and algebraic group scheme if those are schemes, and so on. So what I'm showing you is just the beginning of a very long and important road in mathematics. So for an abstract group, you know what is meant by action. Okay, I'm not going to repeat the rules. You know what are the rules. Okay. So the extra thing needed is this is continuous. This is action. Action as abstract group, which you know what it means. This is a topological group. This is a topical space. And the map is again to that same topical space. And so you may say, to start with, any small g gives a map from x to x, which is a continuous map. Is this map a homeomorphism? Tell me. Yes, it is. Correct, right? You are, because G inverse will be the inverse of that, because G inverse is also continuous map. Okay. But that's not all. This G comma X goes to Gx is jointly continuous in G and X. That's the meaning of this G cross X to X being an action. Abstract. Okay. Yeah. Okay, so that's the concept of an action of a topical group, and that leads to the idea of what is a quotient map Q. Okay. So how do you make this quotient map X to X mod G? You know what are quotients of sets by group actions, right? Those are the set of orbits. You have an equivalence relation under which a point is equivalent to another point if there is a group element which carries the first point into the second. So this is an equivalence relation. So G cross X to X action induces an equivalence relation on X. What is the equivalent relation? X is equivalent to Y if there exists G belonging to G such that Xg is equal to Y. Now you check, why is this what identity? Because E times X is X, therefore everything is equivalent to itself. Why is it symmetric? If G times X is Y, then G inverse times Y is X, and so it's symmetric. Why is it transitive? Why group multiplication? So this quotient means this map, X to X mod this equivalence relation. That is the quotient. Okay. What is its universal property? Now, what topology do you give it? Give this the quotient topology. Meaning open sets, open subsets of X mod tilde are all those whose inverse image in X is open. Okay. What is the universal property of this construction? The same universal property of any quotient. So I have this X to X mod G, and suppose I have any other continuous map to Y. So this is my quotient map Q. This is some other map. Let's call this map var phi. With var phi should have the property that var phi of X should be var phi of Gx for all G belonging to G and X belonging to X. If that happens, there should exist a unique continuous map here, making this triangle commute. And that was the universal property of this quotient construction of an equivalence relation. So that equivalence relation is described like this, and therefore this X mod G has this universal property. Now we come to a very important definition called proper action. So now I'll define a map which at first sight will look strange to you. I go from G cross X to X cross X. and the map is action cross the second projection. So it takes gx and sends it to, well, first is the result of the action, which is gx, and next is the result of the second projection, which is x. So it sends g comma x to gx comma x. So we say that an action a g cross x to x of a topological group on a topical space X is proper if the map A cross P2 from G cross X to X cross X is proper. Now here I am going to write in red dark letters. Does not mean that A from G cross X to X is proper. Exclamation mark. Okay, you may think this definition is a nice definition, but that will not be a nice definition. This is a very nice definition. It has a very simple use. That's what motivates it, which is clear from the next property. Suppose I have some action. Here it seems to be called M. There the action is called A. So suppose I have an action G cross X to X of G on X, and suppose it is proper, then X cross G is Hausdorff. Do you see the proof? So by now you know that in order to prove Hausdorff, it's useless to, it's not so nice trying to take 2 points and show they have disjoint neighborhoods. It's much easier to use the diagonal. Okay. So I take X to this quotient, X mod G. Now I take the map X cross X to, this is the map Q, X mod G cross X mod G. I send X comma Y under this map to what? The equivalence class of X. How do you show the equivalence class of X? Like this, perhaps this. Which means simply Qx and Qy. This is the map Q cross Q. So if I have the map Q, I have the map Q cross Q. Now I'm going to ask you a simple question. Inside this, take the diagonal of X mod G. What is its inverse image here? Okay. The inverse image here is the equivalence relation R. Okay. Yeah. This you can see for anything. Take any quotient by any equivalence relation and take the product map. And the inverse image of diagonal will be the equivalence relation. And so if this action is proper, this equivalence relation is the image of G cross X to X, right? X cross X. What is the image of this? The image of this is the graph of the equivalence relation. Image of A cross P2 equal to the graph R of the equivalence relation. Gx is equivalent to x. This equivalence relation has this graph, and that's just the image of this because it's producing Gx and x, two things which are equivalent exactly when they are image of this. So if this is proper, then R is closed. inside this. And so the inverse image of this is this equivalence relation. Okay. And so if you remember, since this is quotient topology, this is closed here. The inverse image of this is this, which is closed here. Therefore, by definition of quotient topology, this is closed here. And therefore, X mod G is Hausdorff, because its diagonal is closed. So directly properness gave you this. Okay. Now let's show that if G is compact, then every action of G on a Hausdorff space is proper. So again, very pleasant factorizations, that's all. So you recall we proved that when X is compact, any map from X to anything is proper by factorizing it via graph. Just a few minutes ago we did that. Okay, so I have this map, the action is a map. Now what action has been called N? Okay. The action. Take its graph. So how does one take the graph of anything? Remember that if I have any A to B, any map F, then the graph gives a factorization. You go from A to A cross B, and from there you go to B, take this to be the second projection, and take this to be the map. Small a goes to small a comma FA. And this being the projection, it sends A comma B to B. Okay. So if A is compact, then this map is proper. And when is the graph closed? We have proved that if B is Hausdorff, then the graph is closed because graph is the inverse image of the diagonal of B under A cross B to B cross B. If I take the diagonal of B, its inverse image is the graph. So if this is closed, its inverse image is closed. So this is obviously the graph is obviously isomorphic to A because we can project it back to A. That's the inverse to the graph map. All this we have spoken before. And so by applying it to this, I'll get a map from G cross X to G cross X cross X. What is the map? Gx goes to, keep it as it is and then send it to where it is going. So Gx, Gx. This is the map. Okay, I'm copying this formula. And from there, I'm projecting on this. Now I'm projecting on X cross X. Projection on the second and third factor. Why is this projection proper? Because G is compact. Because G is compact, G to a point is proper, and therefore if I take further product with anything, that is proper. Is proper. Therefore proper. And this is the graph. Okay. And X was Hausdorff, so this is a closed embedding. Okay. This was a mapping to X. We used Hausdorffness of B, so B is X here. So this is closed embedding, this is proper, so this is also closed embedding is proper. So this is a composite of two proper maps, and where is it going after this projection? It is going to X comma Gx. This was the map. Well, with the two factors interchange, we wanted the map Gx comma X. So if you want to take its isomorphism with itself of X cross X, which brings the interchanges the two factors and makes them Gx comma X. Okay, so we have proved this. So every compact group action is proper. And if you look at standard differential geometry or physics, there are very large number of compact groups like orthogonal group, unitary group, and whatnot operating on various manifolds and whatnot, which are Hausdorff manifolds. And then all those Lie group actions are going to be proper because of this proposition. But the simplest example of compact is finite. So this shows that any action of a finite group is a discrete topology on a Hausdorff space is proper. So this brings us to an old terminology called totally discontinuous action. If I have a discrete group acting on Hausdorff space, and if that action is proper, it's called totally discontinuous action in old topology books, which were written before all this technology came about. So my question to you, is the action of Z by translation on the real line R a proper action, and what is the quotient? This is homework. Okay. So from here onwards, let's stop the lecture, and if I don't finish it, I'll continue this topic tomorrow. I want to apply topology back to mathematics. So if you remember my grouse of how mathematics gets divided, chopped up into algebra, analysis, topology, number theory, blah, 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 for convenience of studying, but then you have to put it back together, and the putting back together doesn't happen sufficiently. So I want to put back together these things to something which you know. Finally, all this should apply to something which you know from your 12th standard and should be able to prove something nice about it. So I have chosen, so I was thinking yesterday, what can I show? And I thought this is a very simple example which I can show. So I'm doing it. Okay. So I'm going to apply all our proper and quotients and all such theory, factorization, arrows, blah, 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 to study of roots, relation between roots and coefficients of a complex monic polynomial. So suppose I have some complex numbers. Now my color seems to be this. Okay. So let's take Z1 up to Zn, some points in Cn. Okay. So this is C. This comes here like this C. So if I have some complex numbers, well, why did I say Cn? There is a point of, points of C. All right. So let's take n complex numbers. Now there is a monic polynomial which has exactly these roots, namely take t minus z1 into t minus z2 into t minus zn. Then f t is 0 exactly when one of these factors is 0, which means t is equal to z1 or t equal to z2, blah, blah. So the zi's are the roots of this polynomial, which is monic. Now you multiply it out. What do you get? You get ft is equal to t to the power n plus s1 t to the power n minus 1, blah, 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 plus sn, where sr is minus 1 to the power r times sigma z, well, I'll have to use some terrible notation, zi1 times zi2 times blah, 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 times zir for I1 less than I2 less than IR. Take some overall such with this one. That is SR. These are called the elementary symmetric polynomials. Have you heard the word elementary symmetric polynomials? Yeah?
Yes, sir.
And you have probably studied them in your algebra course, perhaps?
Yes.
How about in topology course and complex analysis course? Any doesn't matter. For us, it's all mathematics. Okay. So you take these elementary symmetric polynomials and you have to remember the sign. If you don't like the sign here, then you'll have to write minus S1 plus the next one, blah, 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 plus minus, depending on n is even or odd, this product of everything. Okay. You know what they are when n is equal to 2, sum of the two roots and product of the two roots with appropriate signs. Some will have minus. So the functions Si are called the elementary symmetric functions of Z1, Zn. And they are invariant under permutation. This is what is symmetric about them, because if I make any exchange of the Zi's, that simply means I'm interchanging some factors in this polynomial. So the polynomial remains the same because it's commutative here. And so the SI's don't change after this permutation. So they are invariant under any permutation. I seem to have left some space here for you to write the proof. Okay, you write the proof. Now, I have already told you the proof. So now we define a continuous map from Cn to Cn by sending Z1 to Zn to S1 up to Sn. This is a continuous map. Why is this map continuous? Because sum and product, the two maps product from C cross C to C, and the map sum from C cross C to C. This map takes A comma B and sends it to AB. This takes A comma B and sends it to A plus B. These are continuous. And which is why these are built out of those repeatedly. So by all our earlier factorization, universal property of products and whatnot, you can directly use these two facts and show that all polynomials are continuous. Okay. Now the fundamental theorem of algebra says that f is a surjection. Yeah. Why? Because given any S1, Sn, you are able to write a polynomial t to the power n plus S1 t to the power n minus 1 plus. So suppose you are given a point of Cn, that means S1 up to Sn, you are given n complex numbers. You write this polynomial, and we proved some time back that this polynomial has a root. So factor out that root, then that remaining polynomial has a root, and so on. So finally, you will be able to factorize it as t minus z1 into t minus zn. Except you don't know which one is z1 and which one is z2. Take them in any order, and that point maps to the given point. So fundamental theorem of algebra is just the statement that this map is surjective. Okay, so here's the proposition. This map is proper. This is going to be very important. So let's prove this map is proper. We showed that a map from Rm to Rn, where did it go? A map from Rm to Rn, when was it proper? A map from Rn to Rn was proper when this happened. Limit at infinity is infinity. Okay. So I want to show that the inverse image of a bounded set is bounded. This is what I want to show. So bounded set in Cn, the codomain Cn, is the set of coefficients of the polynomial. And the domain is the set of roots. So this amounts to saying that if I bound the coefficients of a monic polynomial, so if the coefficients of a monic polynomial are bounded, then all its roots are bounded. Okay. So have you seen this statement before? So suppose I have coefficients bounded. Now I want to know how large are the roots. So let t to the power n plus a1t plus a t to the power n minus 1 plus an equal to 0. So either t is less than equal to mod t is less than equal to 1, or mod t is greater than equal to 1. Or both. It may be equal to 1, I don't care. So I shouldn't write it as either or. Let me remove the either. Okay. So one of these possibilities is what if mod t is less than equal to 1, you already know all roots are bounded because zi is one of the roots where this is 0. So suppose the root was greater than 1. Then this means that t is equal to or minus t is equal to, I take this to the other side, a1 upon t plus a2 upon t square. Am I writing it right? No, a1 won't have upon t in it. a1 plus a2 upon t plus a3 upon t square plus an upon t to the power n minus 1. So far you guys agree with me? That shows that mod of t, taking mod of both sides, is less than or equal to mod of a1 plus mod of a2 upon t plus mod of an upon t to the power n minus 1. But I know mod t is greater than or equal to 1. So this is less than or equal to mod a1 plus mod a2 plus mod an. And so the estimate that I arrived at is, therefore, t mod t is less than or equal to maximum of 1 and mod a1 plus dot 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 plus mod an. Yeah, because in case it was already less than 1, yeah, I am through. If it is greater than or equal to 1, I do rest of this. So under this possibility, let me show it by some color. Under this possibility, I am doing the rest of it. Because if mod t is greater than or equal to 1, then t is non-zero, of course. So I can divide both sides by t to the power n minus 1 and get it. Yeah. So I have shown that the inverse image of a bounded set is bounded, because a bounded set in the codomain of Cn means all SIs are bounded, which were the A1, A2, whatever. And so the Z1, Z2, Zn are the possibilities of T. These are the S1, S2, Sn, and these are the Z1, Z2, Zn. So if I bound all of these S1, S2, Sn by further bound, if I say that all these is less than or equal to M, then this is also less than or equal to M. Okay. So is it clear to you that this map is proper? We are given a very nice example of a proper map, namely the elementary symmetric function map is proper. This is so important that I am going to give you a chance to ask a question if you have any. So be quick. 10, 9, 8, 7, 6, 5, 4, 3. Thank you. Yeah, no questions. So let's go on. So now let's look at the permutation action of the group Sn on Cn. What is the action? It takes any Z1, Z2, Zn and it sends it to sigma, well, Z sigma 1. Should I call it like that? If my permutation group is acting on 1 up to n. Z sigma n. Okay. Sigma is 1n bijection to 1n. This is a permutation. So given a permutation, I can use that permutation to interchange my coordinates. So this is the action. And now the map is invariant under the action of Sn, clearly, on the domain of F. Okay. So here is Cn, here is Cn, and you recall that Z1, Zn is going to all that S1 of Zi's, S2 of Zi's, blah, 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 Sn of Zi's. So if I act by permutation, I'm changing the order of Z1 up to Zn, but that doesn't change these functions. So if I take the map from here to here and call it the map sigma, okay, which is sending Z1 up to Zn to, oh, came in the wrong place, Z sigma 1, Z sigma n. So this is a map to Cn, and this is F. Then this triangle commutes. Directly take the symmetric functions or permute them and take symmetric functions. It is the same. That's the meaning of symmetric functions. This F is invariant and the action of. So now my claim is that this map F, this map that now we have, F from Cn to Cn, is the quotient Cn to Cn mod Sn. Sn. So in general, quotient looks very funny. I have this Cn and I have Cn mod Sn. I am saying that this fellow is nothing, and I have the map Q, and I have its abstract description, put together all equivalence classes, give it some abstract topology, and I don't even know how that space really looks. And here it is saying that this is a very nice space you knew all along. It turns out to be Cn itself, and the map Q turns out to be just the elementary symmetric function map. Okay, so if you want to prove this, we want to prove that it has a universal property. So if I take Cn to Cn, and I take this map F, and I take any map to any space Y, map phi, which is Sn invariant. Okay. See, this is said theoretically the quotient because exactly all orbits come together. What are the possible points upstairs? There are factorial n points upstairs unless some roots coincide, because the group Sn acting on Cn is not fixed point free. It can have, or it's not a free action. There can be isotropy at points. For example, the point 0, 0, 0, 0 or 1, 1, 1, 1, whatever is fixed by everything and so on. But this is said theoretically the quotient. This is clear. And so there is a map. There exists a unique map. The only question is, why is it continuous? This is continuous because F is proper. Because F is proper, it is closed. Yeah. Now, to show it is continuous, I have to show that the inverse image of any closed set here is closed. But if I take a closed set here, its inverse image here is closed because this map is continuous. And this map being proper is a closed map, so its image here is closed. And the inverse image of this here is obtained by first taking the inverse image here and then taking the inverse image. Huh? So that's why it is continuous, and that's why it has the universal property of quotient. The factorization is unique because said theoretically that's the only thing possible. Okay. Now, I will further say that F is an open map. It's not only a proper map, it's an open map. The reason is very simple. Any group quotient is open because you see, if I now, Roshni, pay attention, this uses your favorite concept, saturation. So if I take any open subset of Cn, the saturation of any open subset U of X under G action on U on X is open. And this is the reason why, if I take its image and I take its inverse image, that is the saturation, and that's open. And why is the saturation open? Saturation means all those points, it should contain all those points which are equivalent to points inside here, because that is simply the union over G belonging to G of GU. This is the saturation. And this is, each is open because each small g induces a self-homeomorphism of G. So G times U is open, and union of open sets is open. This is open. And this is the saturation. And this shows that if I have any open set, I want to take its image, I may first take its saturation and then take its image, and saturation is open as the inverse image of its image down there, and therefore the inverse in the set down there is open by its being quotient topology. Okay. So all this I want to apply to the following question. Okay. And this question is, if we change the coefficients of a polynomial, suppose I have a polynomial here, ft equal to t to the power n plus s1 t to the power n minus 1 plus Sn, and which you know factorizes as t minus z1 blah 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 t minus zn. Then you know the Sn's are the SI's are the functions of the ZI's, but ZI's are not the functions of SI's, right? Because I don't know in what order to write them. The factorial n possible orders if they are distinct, otherwise somewhat less. So if I vary each one of the S1, S2, Sn slightly, do the Zn's vary slightly? What does this mean? Because it's not even a function of these. So we want to make this statement precise and prove it. Prove it using what we proved here, that this morphism is proper and whatnot. We'll make this statement precise and we'll prove it. And that will be a topological proof. But then we'll give a complex analytic proof also using Cauchy integral formula fundamentally. So I have run out of time, and so this will be the last topic tomorrow. And the rest of tomorrow's lecture, we will go through all the earlier 23 lectures. Tomorrow is 24th lecture. We'll go quickly through all 23 lectures. And in case you guys are interested and ask, and I will not do it till you ask, I can give you some suggestions for further reading. Okay. So that's it for today. Any questions? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. So there are no questions. Okay, Pawan, you can stop the recording. See you tomorrow at 3:30.